Once again, I welcome in the course of Foundation Engineering. So in the last class, I have discussed about the what is the different types of machine and then different types of machine foundation, and after that important terminology used in the machine foundation, and after that design criteria of machine foundation. And after that I have discussed the free vibration and forced vibration. In free vibration, I have discussed one case, that is mass spring model. So today I will discuss the Mass-spring-Dashpot model in free vibration, and then I will discuss the Mass-spring-Dashpot model in forced vibration and Mass-spring model in forced vibration. So now I am going to discuss the Mass-spring model in the forced vibration. So Mass-spring model, Mass-spring model in forced vibration. So in forced vibration there will be the external force. So let the external force is equal to F naught sine omega t. So if I make the model, let us assume this is the spring and a rigid body mass m, and the external force is acting F naught sine omega t. So if I write the equation according to D'Alembert principle, so it will be m z double dot plus k into z is equal to external force is F naught sine omega t. So let z is equal to az sine omega t. So if I derive the, so it will be z dot is equal to az omega into cos omega t. Similarly, z double dot can be written as minus az omega square sine omega t. So if I put the value of z double dot and z in equation 1, so put the value of z double dot and z in equation first. So it will be m into minus az omega square sine omega t plus k into az sine omega t is equal to F naught sine omega t. So sine omega t is common, so it will be cancelled. So we can write minus m az omega square plus k into az is equal to F naught. So if I take common az, so it will be az into k minus m omega square. So it will be k minus m omega square is equal to F naught. So we can write az is equal to F naught by k minus m omega square, where az is the amplitude, F naught is the external force, and k is the spring's constant, and omega is the frequency, and m is the mass of the rigid body. So we can write az is equal to F naught by k divided by 1 minus m omega square by k. So we can write az is equal to F naught by k divided by 1 minus omega square divided by k by m. So we can write let, so this F naught by k is the delta st, static displacement. So we can write Az is equal to delta st divided by 1 minus, and we can write omega square divided by omega n square. So we can write omega square divided by omega n square. And we know that the ratio of frequency to the natural operating frequency to the natural frequency is frequency ratio. So we can write Az is equal to, this is also the expression we have to remember, or we can write Az is equal to delta st divided by 1 minus r square. So we can write Az by delta st is equal to 1 by 1 minus r square, and Az by delta st is called magnification factor. So Az by delta st, Az by delta st is, let us assume this is n, is magnification factor. So we can write n is equal to Az by delta st is equal to 1 by 1 minus r square. Here r is the ratio of omega by omega n, or we can write frequency ratio. Az is the amplitude, delta st the static displacement, and n is the magnification factor. So we can see that the magnification factor is the ratio of amplitude to the static displacement. So if I see if the value of frequency ratio is unity, then the value of magnification factor will be infinite. And if the value of r is, or frequency ratio is less than unity, then there will be a definite value of n. So here we can see that this is the graph between the magnification factor and frequency ratio. So if the value of r, here we can write this is frequency ratio and this is the magnification factor. So if the value of r is equal to 1, so we can see that the value of magnification factor is equal to when r is equal to 1, so the value of magnification factor is infinite. And here we can see that when the frequency ratio is less than 1, then we can use this value of magnification factor, and when r is greater than 1, then we can use this value of magnification factor with different value of damping ratio. What is damping ratio? I will discuss in the later in the next slide. Damping ratio actually is the ratio of actual damping to the critical damping. So the third model that is I am going to discuss, that is Mass-spring-Dashpot model. And firstly I will take the free vibration, means there will be no external force. So if I make, this is the spring and this is the dashpot. So this is the Mass-spring-Dashpot model, spring constant K and damping constant C. So we can write the equation according to D'Alembert principle. So according to D'Alembert principle, so inertia force is m into z double dot plus spring force is k into z plus damping force is c into Z dot is equal to external force. So there is no external force. So we can write mz double dot plus cz dot plus k into z is equal to 0, or we can write z dot plus c by m into z dot plus k by m into z is equal to 0. Let us assume this is the equation first. So we can write here, if I write d square plus c by m into d plus k by m is equal to 0. So this is the quadratic equation in d, where d is equal to d2z by dt square. So here we can, if I solve this quadratic equation, so the root will be, let us assume the root will be alpha and beta. So it will be minus b, so minus c by m plus minus square root of c square by m square minus 4k by m divided by 2. So we can write alpha beta is equal to minus c by 2m plus minus square root of c square by 4m square minus k by m. So if this value is positive, the value of discriminant is greater than 0, then the roots will be real. If the value of this discriminant is exactly 0, then roots are real and equal. And if the value of this discriminant is less than 0, then our roots are complex. So if c square by 4m square minus k by m is equal to 0, then our roots are real and equal. So this is the when c square by 4m square minus k by m is equal to 0. So this is the case of critical damping. Critical damping. So in critical damping, our damping ratio will be equal to unity. So if I solve the critical damping, so what is the critical damping? So critical damping, at critical damping, the value of damping ratio denoted by eta is equal to unity. So what is critical damping ratio? So here if I define damping ratio, so damping ratio is the ratio of actual damping to the critical damping Cc. So the ratio of actual damping to critical damping is called damping ratio, and in case of critical damping, the value of damping ratio will be unity. So what will be the condition of the critical damping? So when the value of c square minus 4m square minus k by m is equal to 0, if I solve this, so it will be c turns to cc, because this is the case of critical damping. So cc square divided by 4m is equal to 4m square is equal to k by m. So here we can write cc square is equal to 4 km, or we can write cc is equal to 2 square root of k into m. So this is the important expression of the critical damping, that is cc is equal to 2 into square root of k into m. So in case of critical damping, the value of damping ratio will be unity. Similarly, here the second case I will discuss, when c square by 4m square minus k by m is greater than 0. So this is the condition of overdamped. damped. In overdamped, our damping ratio value is greater than unity, or we can write C is greater than twice square root of K in case of overdamped. Similarly, when C square by 4m square minus K by m is less than 0, so this is the condition of underdamped. In case of underdamped, our damping ratio value is less than unity. So in machine foundation, generally this case will be practical. So we can write C is less than twice into m into K. So this is the condition of underdamped. Underdamped. So three cases I have discussed. This is the condition for critical damped, condition for critical damping. This is the condition for overdamped. So either the actual damping is greater than 2 times square root of km, or our damping ratio is greater than unity, then this is the case of overdamped. And when our this value c square minus 4m square minus k by m is less than 0, so this is the condition of underdamped. So the solution of this equation first, we have written the equation mz double dot plus cz bar plus kz is equal to 0. So if I write the solution, so solution of equation first. So solution of this equation first can be written as z is equal to a e to the power minus I omega nd into t divided by 1 minus eta square sine omega nd t plus alpha. So this is the solution of equation first, where omega nd is the natural frequency in the case of damping, and eta is the damping ratio. So here, where a and alpha are constant, omega nd is the natural frequency, natural circular frequency in the damped case. And this omega nd can be written as omega n square root of 1 minus eta square. Omega nd is equal to omega n into 1 minus eta square. Similarly, if I write the expression of magnification factor, so magnification factor n can be written as n is equal to 1 by square root of 1 minus r square to the whole square plus twice eta r whole square. So this is the expression of magnification factor, where r is the frequency ratio, eta is the damping ratio, and with the help of this we can write the magnification factor. So r is the frequency ratio omega by omega n, and eta is the damping ratio. It is the ratio of actual damping to the critical damping. So with the help of that we can compute the magnification factor for the Mass-spring-Dashpot model in free vibration case. So let us discuss the another case, that is mass spring dashpot model in forced vibration case. So the fourth case is mass spring dashpot model in case of forced vibration. So if I make the model, this is the spring, this is the dashpot, this is the mass and external forces applied, that is F naught sine omega t C K. So if I write the equation, so it will be mz double dot plus c into z dot plus k into z is equal to F naught sine omega t. So it can also be written as z double dot plus c by m into z dot plus k by m into z is equal to F naught by m sine omega t. So the solution of equation first, solution of this equation can be written as z is equal to F naught by k into sine omega t plus alpha divided by square root of 2 into c by cc into f by fn whole square plus, it can also be written as 1 minus f by fn whole square to the entire whole square. So the maximum value of displacement can be written as z max is equal to az is equal to, the value of this maximum value is unity, so f naught by k divided by square root of 2 into c by cc into f by fn whole square plus 1 minus f by fn whole square. And we know that the value of c by cc is the damping ratio, and similarly f by fn or omega by omega n is the frequency ratio. So if I put the value of c by cc and r in this equation, so we can write az is equal to f naught by k divided by square root of this 2 into eta into r, so it will be 2 eta r whole square plus this f by fn is the frequency ratio, so we can write 1 minus r square whole square. And we know that this f naught by k is the static displacement, so we can write as delta st divided by 4 eta square r square plus 1 minus r square whole square. And az by delta st is the magnification factor, or it is also called dynamic amplification factor. So it will be 1 by square root of twice eta r whole square plus 1 minus r square whole square. So the expression of this magnification factor, so n is the magnification factor or dynamic amplification factor, and this value of n can be written as az by delta st is equal to 1 by square root of twice eta r whole square plus 1 minus r square whole square, where eta is the damping ratio, r is the frequency ratio, and az is the amplitude, and delta st is the static displacement. So let us take one problem based on this. A foundation block of weight 30 kilonewton rests on a soil for which stiffness may be assumed as 25,000 kilonewton per meter. The machine is vibrated vertically by an exciting force of 3 sin 30t kilonewton. Find the natural frequency, natural period, natural circular frequency, and the amplitude of the vertical displacement. The damping factor is 0.5. So damping factor is nothing but it is the damping ratio. So firstly we have to identify whether it is a free vibration case or forced vibration. So we have the external exciting force is given, that is F naught sine omega t is equal to 3 sine 30 t, means F naught is equal to 3 kilonewton and omega is equal to 30 radian per second. Mass is given, mass is equal to how much? 30 kilonewton. So it will be 30 into 10 to the power 3 divided by 9.81. So it will be 30 into 10 to the power 3. So 30 into 10 to the power 3 divided by 9.81. So it will be 3058.1 kg. So we can compute the value of natural circular frequency. So natural circular frequency is omega n is equal to square root of k by m. So stiffness is given, spring stiffness is 25,000 kilonewton per meter. So 25,000 kilonewton per meter. So it will be 3058.1. So it will be 25,000 divided by 3058.1 into 10 to the power 3. Here 10 to the power 3. So it will be square root of 25,000 into 10 to the power 3 divided by 3058.1. So it will be 90.42 radian per second. So natural frequency is natural circular frequency is coming 90.42 and operating frequency is 30 radian per second. So now we can compute the natural frequency in cycle per second, that is 1 by 2 pi square root of k by m. So it will be 1 by 2 pi and square root of k by m, that is omega n we have already computed, that is 90.42. So it will be 90.42 divided by 2 pi. So it is 14.39 cycle per second. Second part, we have to compute the natural time period. So it will be 1 by Fn. So it will be 1 by 14.39. 1 divided by 14.39. So it is coming 0.069. Similarly, we have to find we have already computed the natural frequency, natural period, natural circular frequency, and the amplitude of vertical displacement. So amplitude of vertical displacement, that is n is equal to az by delta st. So az can be computed as n into delta st, and delta st is f naught by k. So firstly we have to find n. So n is equal to 1 by square root of 1 minus r square whole square plus twice eta r whole square. So firstly we have to find the frequency ratio. Frequency ratio r, that is operating frequency by natural frequency. So operating frequency is 30 and natural frequency we have computed, that is 90.42. So it is 90.42. So 30 divided by 90.42, 42. So it is coming 0.332. 0.332. Similarly, damping ratio is actual damping by critical damping. So actual damping ratio is given, that is 0.5. So damping ratio is 0.5. So magnification factor can be computed as 1 divided by 1 minus 0.332 whole square plus 2 into 0.5 into 0.332 whole square. So it can be computed as, of course it is square root. So the value will be, the value of n is equal to 1 divided by square root of 2 into 0.5 into 0.332 whole square plus it will be 1 minus r square. If I compute 2 into 0.5 into 0.332 whole square plus 1 minus r square, so 0.332 whole square. So it is coming 1.053. So the magnification factor is 1.053, and delta st can be computed as f naught by k. So f naught is 3 kilonewton. So 3 kilonewton divided by the value of k. So k is 25,000. So it is 25,000 kilonewton per meter. So kilonewton per meter. So it will be in meter. So if I compute in mm, so it will be 1000. So 3000 divided by 25,000. So it is coming 0.12 mm. 0.12 mm. So amplitude can be computed as is equal to, amplitude can be written as n into delta st. So it will be n into delta st. So n is 1.053 into 0.12. So it will be into 1.053. So it is coming 0.12636 mm. So in this question I have computed the different parameter like natural circular frequency and natural frequency, time period, and amplitude. So let us take the another problem, and this question is asked in Engineering Services Examination 2007. A machine and its foundation weight 981 kilonewton, and has a spring constant K is equal to 10,000 kilonewton per meter. What is the value of damping coefficient if a system is to be critically damped? Take the value of acceleration due to gravity is 9.81 meter per second square. So here, firstly I will compute the mass of rigid body, that is 981 kilonewton. So 981 into 10 to the power 3 divided by 9.81. So it will be 10 to the power 5 kg. Spring constant is given, and in case of critically damped, in case of critical damping, the value of damping ratio will be unity, and the critical damping expression is twice 2 into m into k. So if I put the value of 2 into a square root of 10 to the power 5 into a spring constant is 10,000. So it will be 10,000 into, we can write 10 to the power 4. So this will be 2 into 10 to the power 12. So it will be 2 into 10 to the power 6 kilo Newton second per meter. Newton second per meter, or we can write 2000 kilonewton second per meter is the value of critical damping. So if I see the option, so it will be option C is correct.